Now let's, just like the discrete case, actually, let me not say it again, just like the discrete case, because it's actually the whole scenario is a discrete case, but it's just changed for a continuous case. So we are talking about, we are introducing a couple of common distributions, but this time for continuous random variables. So it's just like, as I said, like learning a new language. So the first vocabulary in terms of continuous random variables that we are going to learn is the continuous uniform distribution. Just like the discrete uniform distribution, where you had between A and B, if you recall, we had with equal usually intervals, we had equal probability mass functions. It's the same thing here, but this time we have an uncountably infinite number of elements here. Therefore, we have a continuous line, and this line is going to be 1 over b minus 1 probability mass function. Why the idea? It's very simple, because when you take the integral here, this is going to be equal to, let's call this the unknown, let's call this h. This is the height, which we do not know. If we integrate it from a to b, this is going to be equal to h times b minus a. And note that this should satisfy the criteria that the result should be equal to 1. Therefore, h, this height, should be equal to 1 over b minus a. Therefore, the probability density function is going to be 1 over b minus a. So that's it. So the whole for the probability continuous uniform distribution, this is the definition of this density. Note that the interval also should be given. Otherwise, one may tend to think that this goes to infinity, which is meaningless here. All right, so the expected value for this case without proof, but let me just show you how this is done and do it as an exercise. I won't even show you this as a bonus video. It's going to be just put these values here. So it's going to be x times the probability density is 1 minus BA, it is constant, times dx, and it's going to be expected value of x, let's say, and this is capital and this lowercase, between a and b, x fx dx. And if you do the calculation, actually it's going to be 1 minus b minus a times x squared over 2 ba. And when you do the calculation, it's going to be b squared minus x squared over 2 times b minus n. This can be written as b plus a over 2ba, where this cancel and you obtain this result, which is straightforward. And also heuristically, it makes very much sense if we have, let's say, a continuous random variable between a equals 10 and b equals 20, the expected value is going to be just the middle way, which is going to be 50. For variance, I leave the derivation to you. Please derive the same logic, but this time you use the formulation for variance. All right. Just this one. Now comes, I think, the most important distribution that actually we are going to devote the second part of this course entirely. And it is also something that maybe you do not use this term as normal distribution, or Gaussian. It's also called Gaussian distribution. Is this somewhere written here? No, but let me write it. This is also Gaussian distribution. What usually you call as curve is this Gaussian distribution, because it looks like, well, actually everything is mathematically a curve. This is more like a bell, maybe bell-shaped curve, you should say. Okay, I'll come to that in a couple of minutes. So this is the normal distribution, which is the most important distribution. There are a couple of theoretical and empirical reasons for that. Well, the point is, well, I'll come to that central limit theorem later. And this central limit theorem is going to be the reason why Gaussian distribution is the most important distribution. But for the time being, let's go over this. The probability density function of Gaussian distribution, however, is probably the most complicated one, the distribution that you have seen up to this point. As you can see, it is, well, let's take it term by term. 2 pi in square roots. This is actually a constant, no big deal. Here we have something called sigma. And note that this sigma will correspond to standard deviation, but do not take it as standard deviation yet. It's going to be x, the random variable that we are interested in, is going to be subtracted from another random variable. It is mu, and it's going to correspond to expected value. However, again, do not think about it as the expected operator yet. Just take it as a parameter and divide it by 2 sigma square. And here the domain is going to be the whole real axis. So it's not going to be going to be confined between 2 finite limits. And the parameter values here is, are there any subject constraint for parameter values? For mu, there is no constraint. The only thing is that it should be a real number. The sigma is, yes, it should be a non-negative real number. Now here's the important point. When actually we are not going to do any calculations using the integral, using this fx Gaussian distribution. Like we are not going to find, for instance, the expected value using x fx dx or variance, or even we are not going to find the probability using the integral between any 2 boundaries. So hopefully you are not going to feel the need to integrate or put this probability density function inside an integral and do mathematical operations. That's a nice thing, but we are going to have an alternative. So what is the expected value of this whole quantity? Skipping the algebraic details, expected value is equal to mu. Well, you may say that it was already mu, but actually I could have written this whole expression very easily like this. If I had written like this, then you wouldn't have realized that this is going to be mu, this is going to be a. Then I would have written here as b. Maybe this is a better or actually more friendly or pedagogically better way of introducing you to Gaussian distribution. Here the parameters are a and b. Expected value of this distribution is b, and the variance of this distribution is going to be equal to a square. And it's exactly because of that reason this a is replaced by variance. So it's going to be, since it's going to be sigma square, we just write here sigma, and there's also the sigma here. I should have also replaced it with a, and b is also replaced with expected value ups, expected value mu. So this form is this is why this form is shown. So it also comes with this package. So there is inside this form, this information also exists. And this whole distribution is shown with this couple. Normal distribution, mu and sigma square. It's like binomial distribution. Recall we had n and p, number of trials, probability of success of each trial. Now this is going to be n, so we usually show it with x is distributed. So x is distributed like that. X is distributed normally, Gaussian distribution with mean mu and with variance sigma square. All right. So for instance, this is all. Each of them is good. There are 4 Gaussian distributed random variables here. This one is, if we call this 5 on the real axis, here this is going to be the both mode, median, and also mean of this distribution. Since this is symmetric distribution and this is going to extend to minus infinity and plus infinity here, they are not going to die out here at certain points. They are going to be very small, yet still non-zero values until x goes to plus and minus infinity. Here the median or the mode or just the middle point here is going to be also mean. So if we are talking about another Gaussian distribution, so this distribution is going to be normal distribution with 5 and 1 variance. Let's call it square like that. Although 1 square is straightforward, it's easier to see. Now when it comes to, for instance, what is the shape of 5, 2 square, if you ask, then you have the same distribution, the highest, well actually maybe the highest point seems to be here, but it's because of my bad drawing. Again, the mode or median of this distribution is going to be here, but it's going to be a flatter distribution. compared to the other one. It's going to die out slower. Why? Because variance is actually 4 times, or standard deviation is 2 times higher compared to the other one. So basically, the moral of the story, if the mean of the distribution, it does not change, but the variance changes, depending on the magnitude of the variance, the distribution is going to be more broader, or is going to be more like a spike. So as this variance goes to 0, for instance, if it's a very small value like 0.001, then I don't know if I can show it, but it's going to be a very spiked thing such as this one. Well, this was, as you can see, awful, but that's the best that I can do. Okay, what if you take the variance constant, but you change mu? So what I would say is, for instance, 20 and 1 square. Variance is constant, mu has changed. So it is just like, probably you have done this in preparing reports in Paint. It is just like copy and paste approach. You cut this and bring this whole distribution till its center, its mode, its median is at 20. Well, practically, actually, you cannot cut this because there is going to be, as I said, non-zero probability density values here on both sides, but I guess you get the idea. So if you just move this distribution until its mode is at 20, you have this one. So the same distribution with the same the broadness of the distribution. It's the same thing again with this one. So and 5, I'm sorry, 20 and 2 square. So it's this one. Just shifted to the right hand side, and there is this again the same relation in terms of variances here between those two distributions. So that's basically what the probability density function of a Gaussian distribution looks like, and how it changes with respect to its expected value and its variance value. Why am I so much into this compared to probability mass functions of discrete random variables? Because as I said, usually we are due to the integration operator, it is easier to understand the properties of continuous random variables by drawing their probability density functions. And actually, Gaussian distribution, for Gaussian distribution, it's even much more important. So it says, if X is a normal distributed random variable with mu, mean, and sigma squared, then Z is equal to X minus mu over sigma. Please note that it's not sigma squared, because actually otherwise the units will not be consistent. Here, the unit in the numerator and the denominator should be identical so that the resulting value is unitless. So you may, as a chemical engineer, you may think about this like a unitless number, maybe like something like Reynolds number. It's not, of course, in scientific terms, it's got nothing to do with Reynolds number, but as something like a unitless number. So this is going to represent where that X specific value of that random variable is situated with respect to this normal distribution. So, and the resulting this Z is going to be called a standardized normal random variable. This Z will be called. Now the important point, still this is going to be a random variable. Why? Because let's take a look at the equation once more. Z is equal to X minus mu over standard deviation. Now X is a random variable. Mu and sigma are not random variables, they are constants. I mentioned that previously. I tried to emphasize that, maybe in bonus material, I cannot remember, but these are obtained from the random variable, yet once they are obtained from the random variable, they are not random variables, this quantity and this quantity, they are constants. Therefore, actually, you can easily write this as this one, and note that this is going to be here, Z is going to be simply a function of the random variable X, and that function here you may call this A, and you may call this whole thing B. So this is going to be equal to AX minus B. So random variable, we have another random variable which we call it Z. Now what about the properties of that random variable? The expected value of Z here, there is a very short proof here actually, but you can easily show it. Let me just go over the expectation operator here. Expectation operator of z, when you apply the expectation operator on z, is going to be ax minus b. So it's going to be simply equal to a expected value of x minus b. It's going to be equal to, this is expected value of z. Now this is what we know, that the expected value of x is equal to mu. Therefore, now what we know about a is this is going to be mu over sigma, because this is a, minus b is equal to again mu over sigma. Therefore, this is going to be equal to 0. So simply expected value of z is going to be equal to 0. So what we do is our new standardized normal random variable has a mean of 0, which means actually if you take a random value, the random variable takes a value of mu. When you put it here, you are going to obtain the value of 0. And the variance is going to be equal to, I'm not going to go over derivation. If you just go over this derivation, it's very simple. You are going to find the variance to be equal to 1. And also this is going to be equal to the standard deviation. So our z is going to be now normal distributed with 0 mean and 1 standard deviation or variance. And the nice thing is, if you apply this standardization procedure for different normal random variables, you end up with comparable z values from different distributions. That's the question. Okay, the expectation and the variance is found by this way. But what about the distribution of z? Actually, we do something we haven't done previously. We take an x value, right, a random variable, we pass it through here, for this specific case, a linear function, and we find a new variable, random variable z, and we find the expected value variance. Okay, that's great. And we call this another random variable. What about the distribution of this z, this new random variable? Without any proof, I tell you that if x is Gaussian distributed normal random variable, and if you pass this normal random variable through a linear function, such as this one, x minus mu over sigma is a linear function, as I show it here, then z is going to be still a normal variable, normal. This means that actually, if we are talking about a cumulative distribution function, note that capital X corresponds to cumulative distribution, which is equal to probability of z smaller equals z. Well, equal is not smaller or equal to z. This equal sign is not important, as I said. This is also for normal distribution. We represent this using a phi. So phi z from this point on will mean that the quantity here is going to be normal distribution, and we are trying to find the cumulative distribution function value. So it means, actually, it is, as you can show here, whatever the z value here is, it is this area. Actually, this tail goes to, as I said previously, goes to infinity, being non-zero. All right, this, for a standard normal variable, we have a table in your textbook. That's what I'm trying to say. So if we erase this part, this actually in your textbook, the table looks something like this. Depending on the version of your textbook, the coloring and the page numbers may change. So, but it's going to be simply cumulative standard normal distribution. And so an example, let's say that we are talking about a recharge time of a battery, and it is in a laptop, and it is normal distributed with 260 minutes and 2,500 minutes square. So once I tell you this, you should visualize in your mind a single battery, of course, does not need to obey to this value, but the population of batteries is going to obey a mean value of 260. So how much a single battery may deviate from this location, it is actually related with this variance value. So let's do this question, and then let's talk about the details later. What's the probability that a laptop lasts for at least 4 hours? Which means, actually, let's again start with defining our event or our random variable. Please always do it that way. Otherwise, if you just start with x without defining it, I wouldn't be knowing what x is. And it's also good to practice to define everything mathematically. So x is battery life. Mu of this x is 260 minutes. And standard deviation of that x is 50 minutes. That's it. So the question asked is, what is the probability that a single element or observation from that distribution x is going to, is it 4 hours? 4 hours is 240 minutes. I'm very sorry, which is 4 hours. What is the probability of this? Actually, if you write it in terms of hours, I'm sorry, minutes, it is easier to see the relation between this one and this one. So what can we say just immediately? The resulting probability should be greater than 0.5. Can we see that, or can you see that? The idea is simple, because this is mode and also median of normal distribution. And we are talking about some values smaller than this on the left-hand side of this distribution. And what we are asked here is the right-hand side area. Therefore, since this probability will include probability of x greater than 260 minutes, and since mu value is also the median of the distribution, normal distribution, therefore probability here is going to be greater than 0.5. So if you find a value smaller than 0.5, there's surely a mistake. So what I'm trying to say that if you do commit an operation, a mathematical arithmetical error, it's very possible, but at the end, if you find the value to be equal to 0.4, let's say, and if you present that value, note that presenting that value will not only be a result of an arithmetic error, but also a grave statistical error. So you have to be careful with what you are doing. Anyway, so if this were any other distribution, what we would have done would be to put 240 here and put infinity here, then write the corresponding fx here, dx, and integrate. The problem here is this is the Gaussian distribution, which consists of exponential x squared term. Therefore, this is difficult for us. So let's get rid of this part. And what we do here is we are going to standardize this random variable. So in the standardized form, it's going to be z is going to be equal to x minus mu over standard deviation. Therefore, this is going to be 240 minus 260 over 50, which is going to be minus 0.4. Now the great point here is this. Now the equivalent representation here would be this one. These two probabilities will be equal to each other, because once you standardize this random variable, what you do is you change the location of this random variable. So originally, this was here at 240 with a spread of 50. It was something like this. If I can draw this as good as I can. Okay. Something like this. This was the distribution of the batteries. Now what I've done is I have subtracted from 260. I'm very sorry. It's here 260. I subtract x. Given any x value, I subtract it from 260, so I bring this to this point. So it is now like this. All right. Probably they are not going to intersect that much due to the variance values, because it's not that much high. Anyway, without changing the spread, you just move it here. Then what you do, you divide by 50, which is actually, you just make this narrower. And this resulting distribution is going to be the distribution of z, while this one was the distribution of x. And the reasoning is, as I said earlier. So now we are only concentrating on that distribution. Note that the expected value is going to be 0 and the standard deviation is going to be equal to 1. Anyway, now what we need is to find this value. And in order to find this value, we use the table. And let me get rid of these. And in our table, note that what we need here is to find probability of z greater than minus 0.4. So in the table, you just search for the minus 0.4 column here. And you do not end up here. Actually, what we are searching for is we need another significant figure, at least one more significant figure to read this table. This is going to be minus 40. So if you read the column here, you are going to search for the column which is going to read 0. And this is going to be actually this column values is going, for instance, this is going to read as minus 0.49. And this is minus 0.48. Therefore, we are going to search for minus 0.40. And this is the value that we are interested in, minus 3, whatever. So I'm going to write here. No, I'm very sorry. Note that this is not the quantity that we are going to be finding. The quantity that we find here is this one. Okay, something like this. Is there another 4? Yeah, it's going to be another 4. Let me write another significant figure. That's it. Note that this is the cumulative distribution value, which means actually this is f.40. The quantity we are asking for is the complement of this one. This is going to be 1 minus f.40. Therefore, you just insert this value here, and we end up with minus 6 is going to be equal to 554. So, and note that this satisfies the initial heuristics or rationale of our expectation that probability is going to be greater than 0.5. So what we have done here is basically in terms of the original variable, the original distribution were here. The sample mean was at 260 and we were asked to find 240. What is the probability here, or what is the area under this region for any value greater than 0.240? And when we convert this to or map to standardized normal random variable, which is the z, standardized normal distribution in terms of z, now we are talking about, so this is going to be z, this is going to be x, and this is going to be, where are we right now? This is going to be minus 0.4, so it's going to be this area. So again, what we do is we map 240 to minus 0.4, all right? And when we do that, this area here and this area here will be identical to each other. That's the important point. Now, let's give a solid, concrete interpretation of sigma. Up to this point, in different distributions, in binomial, in all of them, I'm not going to repeat all of them, I said that sigma is a measure of spread of our distribution. It's the same thing here, but we can give a very clear meaning when it comes to normal distribution. It's again due to the independence of mu and sigma. For other distributions, sigma is a function of mu. As mu changes, the sigma would also change. So it is difficult to give a concrete meaning to sigma, which is invariant to location of theta. Here, since they are independent, the whole thing will always be this measure I'm going to be talking about will always be the same. What do I mean by that? Given a mu value, the question is this: given a mu value and a sigma value, if you go away from the mu value in positive, in negative directions, a multiple of sigma, how much probability are you going to gain? This is the question. So you are going to find exactly as a multiple of sigma what is going to be the probability of a certain region. As I said, for other distributions, it's of course easy to do. This can be done, but note that for the different mu values, the same k times sigma value will give different probabilities. And it is, as I said, due to the relation of sigma and mu. Here, for instance, if we take, let's say, 1 sigma around mu, this is plus and minus. So if we take an x value from mu minus 1 sigma, mu plus 1 sigma, so that's one standard deviation on the right hand side, one standard deviation on the left hand side. Now what we do is, since our standard variable is our standardized normal variable, is our friend here for normal distributions, we convert this new mu plus sigma as Z1 and mu minus sigma as Z2 as two, let's say, random variable, two standardized random variables. So in this case, I'm sorry, let's go. Actually, since all the menu has changed its location due to my still not very friendly this pen to me. Anyway, so x1 is equal to this one. So when we convert this to z1, you just subtract the value mu plus sigma minus mu over sigma. These will cancel. You end up with +1. And if you do the same operation, z2 is going to be -1, which means in terms of standardized normal distribution, x being equal to between mu plus 1 and mu minus 1 corresponds to z between +1 and -1. That's the great thing about standardized normal variable. Now we got a very clear universal picture of the x values. If you go one standard deviation to the left hand side, whatever the standard deviation and whatever the mu is, to the left hand side and to the right hand side, it's going to always correspond to 1 unit going on the right side and 1 unit going to the left side in terms of standardized normal variable. And in this case, what we need to do is we just look up in that table and we find the cumulative distribution function for -1.00, and you end up with this point about 60 value. And of course, since this is symmetric distribution, now the probability that z is smaller than -1 here is going to be equal to probabilities greater than +1. So you may do those tricks. Since this is symmetric distribution, those two tails will have the same probability. But if you do not believe me, you can try that. This right hand side probability can also be found from the cumulative distribution function value at 1. This is going to correspond to this part here. If you subtract it from 1, you are going to end up with this region here. And you are going to see that these two regions have equal areas, thus equal probabilities. Therefore, the probability that we are in between this range is going to be equal to 0.683. So in other words, you may don't memorize, but keep in mind, I think that's a very good practice. If for 1 unit of standardized random error, standardized random variable moving to the right hand side and left hand side of the of 0 is going to be the corresponding probability is going to be 68. So once if somebody gives you that, again think about that rain example, mu is equal to 6 units and sigma is equal to 2 units. In this case, it means that mu plus sigma, mu plus mu minus sigma, which means x value between 8 and 4. The probability that for any day, rain is going to be between those 2 units with a probability of 68. Now, that's the great thing about this normal distribution. Now, if we multiply this, note that there was a hidden 1 here. Mu plus -1 sigma. What if we take this to be 2 sigma? Of course, you may ask, why not 1.5? You can give any value, but let's be practical. If we are talking about 2 sigma, then Z is going to be between, using the same logic, it's going to be between 2 and -2. And in order to compute the corresponding probability, you then refer to your textbook or any textbook related with having a normal distribution table. You find the probability that x is smaller than 2, x is greater than 2, and the remaining part is going to be the probability that we are interested in. And what we find here is 95.4%, which is a very pretty much high value. That's why in many applications, mu plus minus 2 sigma is used for limits. Later we are going to talk more about that, because it's going to contain 95% of all observations. So if you would like to be more certain of the rainfall, you are going to say that it is highly likely that the next day rainfall is going to be between 6 plus 2 times 2, which is going to be equal to 10. And this is going to be equal to 2. So between 2 and 10, you most likely expect your next day rainfall, next day's rainfall, I may say. But note that still this is a finite, this is a, there is a still non-zero probability of being here and here, and in normal distribution there's always going to be non-zero probability, because actually these z values or x values, but when you convert it to z again, they are going to end up only at minus and plus infinite. They are going to decay to 0 with they are going to decay 0 probability only at as z goes to plus and minus infinite. So using the same logic, if you change this to 1 and then 2, if you take 3 sigma values, then you increase the probability to 99.7%. In this case, what we are interested in is the region which spans mu plus minus 3 sigma. And maybe you have heard these terms 3 sigma or 5 sigma, 6 sigma concept, especially things related with what we call quality control. They are related with this actually approach. How much confidence interval, what should be the confidence interval that we are going to take to control, for quality control of a product, which I'm not going to go into. Maybe I'm going to make a bonus video related with that, because quality control is very much related with this topic, yet still you need to know a couple of more additional things. So for the time being, it's not important. Therefore, we can simply, again, not memorize, because these are all tabulated, but you should have an understanding of this representation. So for different multiples of sigma, such as 1, 2, and 3, you increase your probability more and more to 1, but you never reach 1 for a finite multiple of sigma. Okay, the last thing I would like to talk about normal distribution, at least within the scope of this chapter, is a normal distribution approximations to a number of distributions. This part will give you a glimpse of the reason why normal distribution is that much frequently used in many sciences, in many branches of sciences, because you can approximate other distributions under certain conditions to normal distributions. This is not going to be a whole story, but this is going to give you a glimpse of the power of the normal distribution, I may say. So the first distribution that may be approximated by the normal distribution is binomial distribution. The idea is very simple. X is actually a binomial random variable, let's say. So the parameters are n, number of trials with success probability p. Now we have that condition under which we are justified in using the normal approximation. If the expected value of x, which is equal to number of trials multiplied by p, is greater than 5, and this is going to be the expected number of successes, or expected number of failures, where n is going to be number of trials, again 1 minus p is going to be equal to q, which is the failure probability. So this is going to be the expected failure probabilities. If both of these quantities, if both of these measures are above 5, and this is usually going to be the case if n is a large number, the number of trials is large, then we can use this approximation. This is the standardized normal distribution definition of the standardized normal distribution: x minus expected value of x divided by standard deviation. But note that here x itself is a Gaussian distributed random variable. Although actually, well, this is what the definition of standardized normal distribution is. On the other hand, under these conditions, even if x is a binomial random variable, we can directly use this distribution. Therefore, instead of expected value of x, we are going to be writing the expected value of the binomial distribution random variable, since x is a binomial distributed random variable. And when it comes to variance of the binomial distributed random variable, we just write its variance. So we use the information that is obtained from the binomial random variable in standardized normal distribution. And the surprising thing is that this resulting z computed under these conditions will be approximately a standard normal random variable. And that is the surprise. So if these conditions hold, and practically this corresponds to a large number of trials, if p is a sufficiently large number, I may say, then when you standardize the binomial random variable with respect to its own expected value and its own standard deviation, what you end up is approximately a standard random variable. Well, there is actually a very subtle trick here, and that has got nothing to do with this approximation, with the statistical part here. It is just an arithmetical point that we should consider, but still it's an important, at least it's an interesting point that we need to consider. Here is the idea. Now, x is our binomial distributed random variable. Oh, let me, before going into that continuity correction that that subtle point that I'm going to be talking about, let me give you the motivation for this. Well, this binomial distribution to normal distribution approximation will be valid, but we should realize that binomial distribution is actually a discrete distribution. So this is a discrete random variable. Whereas the normal distribution is a continuous random variable. And what's the big deal, you may say? The very important point is binomial distribution or any discrete random variable is going to have a finite probability at any value within the support of x. So at discrete values, it's going to have non-zero or non-negative, I may say, probability values. On the other hand, a continuous variable, random variable, is described by a probability density function. So at specific points, it's actually going to have zero probability, but there's going to be only non-zero probability or non-negative probability within some, actually non-zero probability is better. There's going to be non-zero probability for certain only regions. So okay, we're going to do the approximation, but how are we going to handle this discrepancy between these two distributions? At discrete values, there are going to be non-zero probabilities, but here there are going to be no non-zero probabilities. So let's try to handle this issue. Let's say that the problem in terms of binomial distribution is given in this form. We would like to, for instance, we have 10 test multiple choice questions, again, the same thing, and we would like to find the probability that the number of correct answers would be less than and equal to 2. In this case, the problem is going to be like this. What's the probability that x is going to be small or equal to 2? So that kind of question is we are at what we have at hand. And in binomial distribution, yes, we can find this solution. What's going to be probability x is equal to 0, probability x is equal to 1, and probability x is equal to 2. You add these values. Now, when you change this x to normal distribution, we have to do this continuity correction to take this point into consideration. What do I mean by that? Now, when we change this, and we are going to do it in a couple of minutes, when we change this x to normal distribution, note that x is equal to 2, or let me put it that way, this one will be equal to this one when we change x to Gaussian distribution. because in Gaussian distribution, just like in any continuous distribution, equal to does not have at a certain point we have zero probability. So whether you use less than 2 or less than or equal to 2 does not make any difference. But actually here for a discrete probability it does. So we are actually trying to include the 2 correct answers. We especially would like that. So how can we do that? So what we do here is a trick, is we add 0.5 to that discrete random variable value. So what we say here is, in terms of discrete random variable x, we are not still, x is not still, I'm sorry, Gaussian distributed. This probability is going to be equal to this probability. Why? Because actually x can only take discrete values. The support of x is how many? For instance, we had 10 trials. So the support of x consists of integers from 0 to 10. Therefore, x smaller to 2, and there is also 3 here. So this set will consist of these 3 members, whereas this set 2.5 x smaller than 2.5 will exactly again consist of these 3 members. So there's going to be no change in terms of probability in discrete probability distribution domain, I may say. On the other hand, at this point, now this is our new x value. Now, when we standardize this, actually, however, in Gaussian distribution domain, we are going to see the difference. So instead of this 2, we use 2.5 for the Gaussian distribution. So what we do is we take x plus 0.5 here, and we write here the expected value and the standard deviation or variance, actually square root of variance is standard deviation, and we would like to, the approximation here in binomial distribution, x is smaller equals x will be approximately equal to probability of standardized random variable z smaller equal to x plus 0.5. Let me emphasize once more. Why do we add 0.5, you may say? Because if you add 0, it's the same number. It's 2 plus 0. If you had added 1, that would be including the next outcome also. It's including next outcome to the event space, which would be wrong, because we would not like this condition, because we don't want x is equal to 3 here. We are only interested x up to equal to 2. So actually what you can do is, we are somewhere between adding 0 to 1. Any point between 2 is accessible in terms of discrete distribution. But when you make it continuous, note that we would like to include this 0 but exclude this 1, right? So therefore, the middle way between them is a kind of, seems like a good choice. There may be better approximations, but that seems to be pretty much sufficient, I may say. So what we are trying to do is just to include this boundary value given in binomial distribution. In binomial distribution, that's not a problem. We can easily include it using the probability mass function at x is equal to 2. But when it's Gaussian distribution, it becomes difficult, so you do this trick. Now, do not take it as we always add 0.5. In some cases, we may subtract 0.5. Why? If, for instance, this is the case, probability x is greater than or equal to x kind of thing. In this case, we are going to, if this is the real axis, it means that, and let's say that this is our x, we are interested in this value, and this value. If you could just convert it using this, these values, I mean the x value to Gaussian distribution, then whether this x value is included or not will be problematic. So what we do is we just pull back the boundary here, not including this x minus 1 value here, but somewhere in the middle. So what we do is we subtract minus 0.5 from this x value and do the continuity, do the standardization procedure. And I think in the third case, this is the really obvious one. If we are interested, especially only if what's the probability that we are going to be answering exactly 2 correct answers. Note that if you convert this to directly to normal distribution, this is going to be meaningless because we are going to be trying to find probability z equal to some certain value, and that is, in terms of Gaussian distribution, has 0 probability. Although this has, of course, non-zero probability in binomial distribution. So what we do here is a very similar strategy, 0, 1, 2. It's going to be such that we are not going to include this member, this outcome, but we are going to extend this to over a region. Therefore, what we do is we take minus 0.5 here, so 1.5 and 2.5. So we consider this range in Gaussian distribution, but we start considering this range in, of course, in binomial distribution. Is the only integer here is 2. But when you change it to normal distribution, it becomes much more important in the calculation. So an example is a very straightforward example. X is a binomial random variable with n is equal to 200, probability is equal to 0.3. What is this quantity equal to? Now, I think first, it is a better approach to try to solve this problem without any approximations. And in this case, it becomes much more evident why we really need these approximations. So it's not just some luxury. So this is going to be basically equal to this. Let me not write this all over again. This is going to be equal to f at probability mass function at 61, 62, and it goes plus f70. And for each of these, you have to write 200 to 61. 0.3 to 61 and 0.7. Okay, if we subtract these, what's going to be 9, I guess. Plus, so we have just handled, actually we haven't handled it because you have to compute this, and you should realize that it's not going to be very easy for typical calculators. And for 62, we are going to be writing 62.3 to the power 62, and it goes like this. And if we have actually extended this range to 100 and or 200, whatever, and if I had made this, let's say, 20,000 or other values, then the problem could have been almost impossible or very difficult to solve using this approach. I mean, so for the probability density function, if you have many trials, the question becomes difficult to solve computationally, because for each outcome, for each discrete value, you have to compute the probability mass function and add them. So the problem is difficult to handle. So can we use, first of all, we should ask the question, can we use the normal probability approximation? In order to do that, we have to check the only condition that we need to check, which is NP, whether this is greater than 5, and 1 minus P, which is greater than 5. Well, 5 is actually determined using an empirical approach. Even if it's smaller than 5, this is close to normal distribution, but 5 is actually is a sufficient boundary to make the result pretty much close to to make the result found by normal approximation very much close to the exact result. So anyway, let's check these conditions. So in order to use normal approximation, first we have to do this check. 200 times 0.3 is going to be equal to 60, which is greater than 5, and 200 times 0.7 is going to be equal to 140, which is greater than 5. That's great. You know that. Okay, so therefore, normal approximation will be valid. Now the normal approximation. We are asked this quantity. At the very beginning, we have to do the continuity correction. It should be such that we are not going to include 60 and we are going to include 70. So we have to change the boundaries. We don't want these boundaries to be exactly at these integer values, because for these cases, it's not going to be obvious for the Gaussian distribution whether it includes these values or not. So what we are going to do is we are going to write this expression. Still, X is binomial distributed. Note that it should be written in such a form that it's going to give the same result in binomial distribution. So this representation, note that if you change this boundary to 60.5, you are going to be still excluding this value, but including 71. And this is what is said here, what is dictated here. And here is dictated, includes 70, but not 71. And this is what it says, actually, 70.5. Now, so this part is what we call continuity correction. I hope I have written continuity correctly. And the next step is going to be the normal approximation. So we are going to standardize the normal variable. So this is going to be approximately equal to probability of 60.5 subtracted from the expected value. Here maybe we should have found the expected value. Actually, it's already been found. It's 60 here. And variance of x is going to be equal to 60 multiplied by 0.7, which is going to be equal to, I think, 21. Yes. Oops. I'm sorry. 43. All right. So this is going to be equal to 60 divided by 43. This is smaller, equal. That value is going to be smaller equal. Note that whether you put this smaller equal here or not, it doesn't make any difference, because whether we include 60.5 is not important. What is important is excluding 60. And this is going to be 70.5 minus 60 divided by 43. And this result is going to be, I'm going to copy here, so please do the calculations. That's smaller than. This is going to be equal to, actually, how can we find this? We are going to be using standardized normal distribution table. And in that table, what we are going to find, let me try to show you what this corresponds to in terms of a graphical representation. If this is a standard normal distribution, which actually doesn't look like a fine standard distribution, but that's okay. So that's 1.62. So 0.008 is going to be here, and 1.62 is going to be here. And what we are interested in is this area. So this area can be found using that normal distribution table as the cumulative distribution function at 1.62 minus cumulative distribution function at 0.08. And how do I find that? It's by this method. Note that, all right, cumulative distribution function of 0.08 is going to be this region, all the tail to minus infinity. This area, including this part. And 1.62 is going to be this point plus that additional region. So it's going to be all the area below z value smaller than 1.62. So it's going to be that region. So if you subtract those two, the resulting, this intermediate region is going to be determined. So if you just check your textbook and find these values, it's going to be minus 447 minus 453. So this is going to, and the resulting probability is 0.450. All right. So the next approximation is going to be employed on Poisson distribution. Actually, this should be expected because actually Poisson distribution is like a continuous version. When I say continuous, I'm not referring to random variable, but I'm referring to the number of trials or the trial procedure, the trialing procedure of the binomial distribution. So Poisson distribution may also be approximated by Gaussian distribution. The idea is very simple. If the expected value of the Poisson random variable, which is actually equal to lambda times t, If this is greater than 5, so we are talking about a certain time range for which the expected number of outcomes during that time range is greater than 5, then we may use the Poisson distribution. And how we may maybe use it, we are going to take the Poisson distributed x, we are going to subtract it from the expected value, and we are going to divide by the standard deviation. Well, please note that variance of the Poisson random variable, it's equal to its expected value, so therefore there are two the identical terms here. Again, with the same continuity correction. So you should be careful adding that delta x or minus delta x thing here, that small 0.5 thing here. So as an example, let's say that x is a Poisson random variable with lambda value 6 particles per centimeter square. So per centimeter square, we can meet on the average 6 particles. So once for 1 centimeter square area, compute the probability x to be smaller than 4. For this question, let's find the exact solution, because we can find the exact solution for this one easily compared to the previous case where exact solution requires adding those 10 terms with very high powers and factorial. So probability of x smaller than 4 is going to be equal to f0, f1, f2, f3, and I think that's all. All right, because it says x smaller than 4. So for each one, if you take the exponential, the Poisson distribution formulation is going to be simply, please check what I'm doing. I'm doing a little bit fast. And the result is 0.1520, 12, I'm sorry. Okay, so this is the exact solution of 4 smaller than 4 events or 4 particles per centimeter square. Now the approximate solution. First of all, we should check whether approximate solution may be applied. So expected value of x here is equal to, where is it? Equal to 6, because we are talking about 1. All right, let's do it formally. Expected value, this is going to be t, and this is going to be equal to 1 centimeter square. So it's going to be 6 particles per centimeter square times 1 centimeter square. These will cancel. It's going to be 6 particles. Note that this is greater than 5, which is suggested by the argument given here. Therefore, normal approximation valid. Now, once we validate it, what we are going to do is we are going to simply write x smaller than 5. We are going to do the continuity correction. We would like to exclude 4, but we would like to include 3. Therefore, we can write x smaller equal 3.5. In terms of Poisson distribution, these two are the same. But in terms of normal distribution, this this is important. Z smaller equal to 3.5 minus the expected value is equal to 6, and the standard deviation is going to be square root of 6. And then we find the result, probability that I should copy again from my notes. The result, this, when you compute this, the result is going to be equal to minus 1.02. And if you check, this is going to be the cumulative distribution function of minus 1.02, and the result is 1587. So this is the approximate result, and this is the exact result. And note that we are very close to this boundary value, that limit value, that 6 particles is very close to 5. On the other hand, we have that much of a very good approximation. So as this number gets larger to 66,000, we are much closer to the exact result.